I gave you this position time graph here, could you tell me the velocity and acceleration of the object? By the end of this video, you should be able to describe the exact motion of the object. To start, if you can understand these following relationships, you can answer any question about a position time graph. We can link position, velocity, and time using the slopes of the graph expressed by this relationship here, and we can use the areas of the graphs to relate the acceleration, velocity, and position by these relationships here. But before looking at graphs in depth, let's define some needed variables. So to start, position denoted by x tells us where an object is related to the origin. So for example, if x equals positive 5 meters, what this means is that you're 5 meters in the positive direction from the origin. So if I draw this x-axis here, x equals 5 just means we are at the positive 5 meters position. Whereas, for example, if x equals negative 5 meters, this means that you're 5 meters in the opposite direction from the origin. So if we draw our x-axis here, this means that you would be on the left-hand side here at x equals negative 5. And one thing to note, position does not equal distance traveled. So if I travel from x equals 0 to x equals 10 to x equals 4, x equals 4 is my final position, but I traveled a total distance of from x equals 0 to x equals 10, so 10, plus from x equals 10 to x equals 4, which is 6. And so my total distance would actually be 10 plus that 6, which would be equal to 16. It looks like I made a small error here, sorry about that, guys. But this is just to emphasize the point that the displacement is not actually equal to distance traveled. They're two different quantities. So next we can define velocity v, which tells us how quickly the position changes. And average velocity is given by this equation here, where delta t is a long duration of time, which is larger than 0.01 seconds. And then the instantaneous velocity is given by this equation here, where lowercase dt is an infinitesimally small change in time. So the instantaneous velocity measures the very small amount of change in this infinitesimally small amount of time. And so one thing to note is an important distinction here. Speed is a magnitude, but velocity is a magnitude plus a direction. So if we're given these two velocities here, they have the same speed, equal to 10, but they have opposite velocities because one is positive and one is negative. And if you label them v1 and v2, v1, the object is traveling at 10 meters per second in the positive x direction, and v2, the object is traveling 10 meters per second, but in the negative x direction. The next thing we can define is acceleration, denoted by lowercase a, and it tells us how quickly the velocity changes. So the average acceleration is given by this equation here, where delta v is the change in velocity, and delta t is a relatively long time interval. Instantaneous acceleration can be written as this, where dt is an infinitesimally small time interval. So visually here, if we're given this velocity time graph, the average acceleration is the slope from t1 to t2, so this longer time interval, and the instantaneous acceleration is the slope of this very small dt time interval. And a very important thing to know here, there's a common misconception with negative acceleration. Negative acceleration does not necessarily automatically mean that the object is slowing down. Whether the object speeds up or slows down depends on the sign of velocity and acceleration. So for example, if the velocity is equal to negative 10 meters per second and the acceleration is equal to negative 2 meters per second squared, 1 second later, the velocity is going to be equal to negative 12 meters per second. So in this situation, the speed actually increases from 10 meters per second to 12 meters per second. So negative acceleration doesn't automatically mean that the velocity decreases. And a key way to remember this is by this table below, where the sign of velocity and acceleration determines if the object speeds up or slows down. With these definitions defined, we can now look at a position time graph. So if we look at this position time graph here, the first fundamental relationship is that the velocity is equal to the change in position divided by change in time. So it's represented by the slope of the graph. And so we can look at what is going on in this case. In our case, the position is increasing at a constant rate. And so therefore the velocity is positive and the acceleration is equal to 0 since the slope doesn't change. The line is constantly going up, so the position is constantly increasing. So for example, if we find the average velocity in this case, you can denote that at our first position here, t1 is going to be equal to 0 and x1 is equal to 0 since our position's on the x-axis. And then we can define this later point as point 2. So at this point here, t is equal to 5 seconds and x is going to be equal to 20 meters. So with that, we can define p1 and p2 as so. If we apply this to our equation, we can write the change in position and the change in time as so. If we apply p1 and p2 here, we can label our times and positions as so, and then we can directly plug these into our equation, and we can do a simple subtraction and then a division, and we find that our average velocity is equal to positive 4 meters per second. And so this is the average velocity during the time interval. And this also represents the slope of the line for the above graph. We can also find the average acceleration given by this equation here. For this example here, velocity for this interval is equal to 4 meters per second. And since the position is increasing at a constant rate, that means the velocity at v1 and v2 are both 4 meters per second. We can write p1 and p2 as so, where the velocity is the same at both points. If we plug both these values in and solve, we find that the average acceleration is equal to 0. And so this is the average acceleration during the time interval. Therefore, that means that when the position is steadily increasing at a constant rate, this means that the velocity is positive, and this also means that the acceleration is equal to 0. And one note on steeper lines, if we're given a position time graph like so, and we have one position denoted by this red line here, and then we have a steeper change in position denoted by this blue line, we can note that at a time t equals 3, it denotes two different points on the subsequent graphs. If we denote blue as the steeper graph and red as the less steep graph, we can find the velocity for the red graph as the change in position over change in time, which they both start at this point here at the origin x equals 0. And so at this later time, t equals 3, the red graph is going to be at 2 meters. So we can plug these values in and solve. And the velocity of the red graph during this time interval is equal to 0.67 meters per second. But if we follow the same process for the blue graph here, they both start at the same position, but the blue graph actually gets to a farther position in the same amount of time. It gets to 5 meters. So if we plug this in and solve, we find that the velocity of the blue line is equal to 1.67 meters per second. So the velocity of the blue is greater than the velocity of the red in the same time interval. And the blue line is a steeper slope. So that means the greater the slope, the greater the velocity. And a second thing we can note is what a horizontal line on a position time graph can tell us. If we have a horizontal line like this on a position time graph, this means that the object is at a position x equals 5 in this example from the time equals 0 to the time equals 5. So this essentially just means the object is stationary, which therefore the consequence of that is that the velocity is equal to 0 since the object's not moving. We can also look at if an object's position is decreasing. So if we look at this position time graph here, where we have a downward slope in the position, we can identify that at time equals 0, the position is going to be x1 equals 5 meters, and then that time equals 5, the position is going to be x equals 0 meters. So it goes from 5 meters to 0 meters. And so if we use our velocity equation here and plug in our values for the 0.2 and 0.1, we end up finding that the velocity is negative. So the resulting velocity for a object with a decreasing position is negative in this case, which means that the object is moving in the negative direction. And this makes sense because we saw in the above situation that the object travels from x equals 5 meters to x equals 0 meters, so position is decreasing. And so now we can look at curved position time graphs. So let's say we're given this curved position time graph here. This is where acceleration enters the discussion here. So if we look at the small point here, the velocity is going to be the slope of the curve. And so at every instant, our velocity is going to be the slope. But since the position time graph is curved upward, this means that the slope is increasingly becoming more steep. And since v is equivalent to the slope, this means that our velocity is increasing as we travel up. And so if we take this example here, the slope at this later point is going to be greater than the slope at the earlier point here. So that means that the velocity at the greater point is going to be greater. And so what does this mean for acceleration? This means that the object is accelerating, but why? If we remember that our acceleration equation is equal to change velocity over change in time, since the slope is steeper up here, we can define this velocity as greater than the velocity before. So if we just give some arbitrary values for these and we plug them in, we find that the acceleration is equal to positive 1 meters per second squared. So the object has now picked up a positive acceleration due to this curved shape in the graph. And so the key property of a position time graph is that if it's curved upwards, the acceleration is positive, as we saw above. But if it's curved downward, that means the acceleration is negative. But one thing I just want you to remember, that negative acceleration doesn't necessarily mean that our object's slowing down. We discussed this earlier. So now we can also discuss turning points in a position time graph. So at this top point here, the tangent is equal to 0. What this means is that at this instant here, change in the position over change in time is equal to 0. Since if we apply the general equation here, for this instant, x2 is equal to x1, that would mean that the change in slope over change in time is equal to 0 for this short instant. And at this top point here, the slope is neither positive or negative, since the object is going in the positive direction and the negative direction. And since velocity is equal to change in position over change in time, on the left-hand side here, the velocity is positive, the position is increasing. And on the negative side, the velocity is negative since the position is decreasing. And this particular motion, a good analogous example is like throwing a ball in the air. So if I throw a ball directly in the air up, the position is going to change like so. And if we drew a diagram for this, the positive increasing direction would represent the left side as the object is increasing in position. And then the top point here would represent the turning point when the object's at its max height between going up and going down. And then as the object's falling down, it would represent the right-hand side. The position is decreasing. And one thing to note, in this situation, acceleration is equal to negative g, and that's what's causing the ball to eventually fall. We start with a positive velocity, and this negative acceleration is causing the velocity to go to 0 at the top and then become negative after it reaches the top. And so a key thing to keep in mind here, that's why velocity equals 0 does not necessarily mean acceleration is equal to 0. At the top, the velocity is equal to 0, but the acceleration is still equal to negative g. So now we start looking at velocity time graphs. And so if we look at this velocity time graph here, two key relationships are that 1, the slope on a velocity time graph is equal to acceleration. And the second thing is that the area under the curve is equal to our change in position, which is our displacement. And so we can start off by looking at the example of a horizontal line on a velocity time graph. And so what this means is that the velocity is constant. But what does this mean for the acceleration and the displacement? So if we define the point 1 and point 2 as so, a straight line means the velocity is constant. And so if we apply the acceleration equation equal to change in velocity over change in time to these 2 points, we find that the acceleration is equal to 0. But what about the displacement? As we said before, the displacement is equal to the area under the curve. We can identify that the side length is equal to 5 meters per second, and then the width here is equal to 5 seconds. So this is going to be our area here, which is equal to our displacement. So if we just apply the area, we found that the displacement is equal to 25 meters. So even though acceleration is equal to 0, the object is still displacing 25 meters since it's traveling at a constant velocity. So that's what happens when the velocity is a straight line. And another situation we can look at is if there's an increasing velocity. So if we have an upward slope in a velocity versus time graph like this, we could denote point 1 at the origin and then point 2 at the maximum velocity. And so in this situation here with increasing velocity from point 1 to point 2, we can address what the acceleration and what displacement will be. First, the acceleration, we can just apply the acceleration equation, which is equal to the change velocity over change in time. So if we plug in the value for the velocity and the time, with the velocity at the greater height being 0.2 and then the origin point being 0.1, we find that the total acceleration from 0.1 to 0.2 is equal to positive 2 meters per second squared. So when the velocity is increasing, that means the acceleration is positive. And what about the displacement? If you remember, displacement is equal to the area under the curve, so it's going to be this area here, represented by this triangle. With our side length here, it's going to be 10 meters per second, and then the time interval is 5 seconds, so we can draw out this triangle here, and then we can apply the simple area of a triangle equation, and if we plug in our two values for the base and the height, and do some simple computations, we get that the displacement is equal to 25 meters. So when the velocity is increasing, the displacement is going to be a positive value. Now we can also address the opposite case when the velocity is negative. So if we look at this velocity versus time graph here, where the velocity goes from being positive to crossing the x-axis and becoming negative, if we draw up this point here where it crosses the axis at time equals 2, and we label this later point here as t2 where it's maximally negative at negative 5 meters per second. When the graph passes the x-axis, that means the velocity goes from positive to negative. And so what does this mean for the acceleration and the displacement? Well, if we apply our acceleration equation to point 2, where v2 is equal to negative 5 meters per second, minus the velocity at point 1 here, where it crosses the x-axis, if we plug in these values here at these 2 points, we end up finding that the acceleration is negative. And this makes sense because the acceleration is represented by the slope. And in this graph here, we have a negative slope. So it makes sense that we have a negative acceleration. And now for the displacement, if we take the displacement between these 2 points here, it's going to be this area element. And so the length is going to be 2 seconds, but the height is going to be negative 5 meters per second since we're below the x-axis. So if we just apply the general formula for the area of a triangle and plug in our values, we get a negative displacement. And so the key insight is that if the velocity is negative, this means that there's a negative displacement. This makes sense since negative velocity means it is traveling in the negative direction. So now with that, we can move on to discussing acceleration versus time graphs. And the one thing to keep in mind is that acceleration will always be a horizontal line on an acceleration versus time graph. So in this example here, the acceleration is equal to 3 meters per second squared from time equals 0 to time equals 4. And the most important relationship for acceleration time graphs is that the area under the curve is equal to the change in velocity. So in our graph up here, the area under the curve is going to represent the change in velocity here. So we can write down that our height, which is our acceleration, is equal to 3 meters per second squared, and then our time interval is 4 seconds. So we get this rectangular box here. And if we just do a simple calculation for the area here, we find that the change in velocity is equal to positive 12 meters per second. And this means if our object is accelerating at 4 meters per second squared for 4 seconds, the change in velocity is equal to 12 meters per second. So if, for example, our initial velocity is positive 3 meters per second, then this essentially means that our later velocity is going to be 15 meters per second, since we have a positive change of 12 meters per second, which can also be expressed by this general equation here. So v2 is just going to be equal to v1 plus our change in velocity. So in general, to summarize, there's three kind of graphs that we went over: position time graphs, velocity time graphs, and acceleration time graphs. And the slope of a position time graph gives the velocity. The slope of a velocity time graph gives the acceleration. And then going backwards, the area under the curve of the acceleration time graph is equal to our change in velocity. And it's also denoted by the integral of the acceleration. That essentially means the same thing. And then also the area under the curve, or the integral of the velocity, is equal to our change in displacement. And so this is why calculus is so deeply connected with physics. By differentiation, it takes us from the position to velocity to acceleration. And by integration, it takes us back from acceleration to velocity to position. So now we can iron out these topics by going over an example scenario. So let's say we have a car that starts at rest and then accelerates at 2 meters per second squared for 5 seconds. And then after, it travels at a constant velocity for 5 seconds. Then lastly, it brakes at negative 2 meters per second squared until stopping. In this scenario, we have 3 stages. So we can start by evaluating the first stage, which we have the car accelerating at 2 meters per second squared for 5 seconds. And it starts at rest, so that means the velocity is equal to 0 at the start. So visually, we can start by drawing our time graphs like so. And so we already know that what the acceleration is for the first 5 seconds. And we know our initial velocity is equal to 0. But what is our velocity going to be at 5 seconds? That's where we can start solving this question. And you can use this equation, or you could have just solved it by finding the area under the curve of the acceleration graph. I accidentally put 5 meters per second squared on the y-axis, but it's actually 2 meters per second squared. So we get the same value here of the final velocity equaling 10 meters per second at time equals 5 seconds. So we can plot it like so. And then from here, we can find what our total displacement is by finding the area under the velocity curve. And if we do that and evaluate, we find that the area under the velocity curve is equal to 50 meters. So that means we displace a total of 50 meters. And assuming that we start at the origin, the change in place is equal to x2 minus x1. So if x1 is equal to 0, that means x2 is equal to 50 meters. So the final position for the object is going to be 50 meters. And then we can draw the slope of the position time graph like so. Because we're accelerating, the position is not changing at a constant rate. Since we're increasingly getting faster, our velocity is increasing steadily. So that means that our slope is going to be curved upward in the position time graph, because remember, our slope in the position time graph is equal to our velocity. So now we start evaluating the second part of this question, which the object after 5 seconds travels at a constant velocity for the next 5 seconds. So we just found that the velocity is equal to 10 meters per second at t equals 5 seconds. So that means that it's going to travel at 10 meters per second for the next 5 seconds. And since it's constant velocity, that means acceleration is equal to 0. Because if you remember that acceleration is equal to change in velocity over change in time, since v2 is equal to v1 in this situation, it's constant, we're going to get acceleration equal to 0. So if we draw our graphs like so, from time equals 5 seconds, time equals 10 seconds, we can start by identifying that the acceleration is just going to be equal to 0 from 5 seconds to 10 seconds. And then the velocity is just going to be a horizontal line since it's constant the whole time. And it's going to be at velocity equal to 10 meters per second. And to draw the position time graph, we need to find the displacement, which is going to be equal to the area under the curve of the velocity time graph. So if we look at the velocity time graph here, it's going to be equal to this rectangle here. So if we just plug in the length and the width of this rectangle and solve, we find that the displacement is equal to 50 meters. And so at time equal 5 seconds, the position is actually equal to 15 meters. So this is going to be our x1 position. And so we just found that the change in position is equal to 50 meters. If we just use the change in position equal to x2 minus x1, we can find what our final position is by plugging in our values here. And if we do that, we find that the final position is equal to 100 meters. And we can just draw a straight line for this because the velocity is constant this whole time. So it's going to be changing position at a constant rate. So now we can look at the last stage here, which is stage 3. And in this stage, the acceleration is equal to negative 2 meters per second squared. The initial velocity during this portion is going to be equal to 10 meters per second. Since we're looking at the last interval here from 10 seconds to 15 seconds, if we draw our graphs like so, we can start off by drawing our acceleration, which is equal to negative 2 meters per second squared the whole time. The first thing we can do, since we need the velocity at t equals 15 seconds, we can do this by finding the area under the curve of the acceleration time graph. So if we find the area under the curve here, we find that the change in velocity is equal to negative 10 meters per second during the time interval. So since we start at initial velocity of 10 meters per second, and we have a change of negative 10 meters per second, change in velocity is equal to v2 minus v1. We can isolate for v2 and plug in our values, and we find that our final velocity is equal to 0 meters per second. So with that, we can draw in our velocity time graph with our initial velocity equaling 10 meters per second, and then at t equals 15 seconds, our final velocity is equal to 0. And then we can just draw a straight line from the initial velocity to the final velocity, since the acceleration is constant the whole time. So the velocity is going to be decreasing at a constant rate the whole time. From here, we can figure out the position time graph by first identifying the displacement, which is going to be equal to the area under the velocity time graph curve. So the area under the velocity time graph curve is equal to this, and so we can draw this triangle here and use the area of a triangle, plugging in our values, solving, and if we do that, we find that our displacement is equal to this. So the position is actually increasing in this situation. And so this kind of illustrates the example of just because we have a negative acceleration doesn't mean our position is also in the negative direction. Even though velocity is still slowing down, it's still positive. So that means that the position is increasing still. And so we can find what x2 is by using the displacement equal to x2 minus x1. And we know that our position is 100 meters at t equals 10 seconds. And so if we plug in that for x1 and we plug in our displacement, we can find x2. And x2 is equal to this. So we can draw that in. And in this situation, we can draw in the curve, and it's going to be curving down because since the acceleration is negative, that means our velocity is consistently decreasing. So that means our slope should be becoming less steep as we get to our final position, since our velocity is slowing down. So that's about it for the example problem. And the last thing I want to do is to go over some common mistakes that people make when dealing with these kinds of graphs. The first common mistake is people think that negative acceleration means slowing down. It doesn't necessarily mean slowing down, as we discussed earlier. The second thing is people think that the position time graph height represents velocity. That is not true. The slope of the position time graph represents the velocity. And then a third common mistake I see people make is that people think that if velocity is equal to 0, acceleration is equal to 0. And this is definitely not true. We've seen with the ball scenario, at the max height, the velocity was equal to 0, but the acceleration was still equal to negative g. And then the last mistake I've seen that's pretty common is that people think that the area under the velocity time graph gives the distance. It does not give the distance, it gives the displacement. And so that's another thing you want to remember. And so just a final summary here, these relationships here are key to solving these problems, where the slope of the position time graph gives the velocity and the slope of the velocity time graph gives the acceleration. And then backwards, the area under the acceleration curves gives the change of velocity, and then the area under the velocity curve gives the change in position. And some key things to remember here is position tells you where you are, velocity tells you how position is changing, and acceleration tells you how that velocity is changing. One last thing, I'm going to leave you with a question here. Comment below if you know the answer. An object's velocity is negative and its acceleration is positive. Is this object speeding up or slowing down? Comment below. Thanks for watching.